Hello U9s and welcome back to Math and Magic. In today's lesson we're continuing with our topic of linear relationships and we're going to be talking about a thing called direct proportion. So by the end of today's lesson we should be able to explain what direct proportion is and solve problems involving direct proportion. Now, just a quick summary of what we did in the last lesson. Last lesson we talked about the gradient. The gradient is a measure of how steep or sloped a line is, and in particular we use this formula which is on the screen here. Rise over run. And so this was the example that we looked at last lesson. And so the rise is how many y units, so units in the y coordinate that we go up or down by. And the run is how many x units or horizontal units we go across by. And so here, all we had to do was we had to divide the rise by the run to get me the steepness of the line. So that's what we looked at last lesson. Today we're actually going to build off of that and talk about a concept called direct proportion. So before we continue with this, let's actually talk about what direct proportion is. So here I have a definition. Direct proportion. Now, two variables are in direct proportion or are directly proportional if the rate of change of one variable compared to the other is constant. Okay, now there's a few words here that we kind of need to talk about so that we can actually understand what this is talking about. The first thing is variables. Now, a variable is a thing that just changes over time. So things that change over time. So things that change over time. And in science, you might remember that word. So in science, you talk about the independent and dependent variable when you do an experiment. So for example, you might be measuring the height of a plant over time. So your independent variable is your time, and then your dependent variable is the height of your plant. So here we're talking about two things that change over time. It could be height of a plant and time. It could be, we're going to talk about this in a moment, but we could be talking about someone running and the distance and the speed. We're comparing two things that change. Now, the second part here is the rate of change. Now, what does it mean for a rate of change? Well, this just tells me how quick a rate of change is. How quickly is one thing changing? How quickly a variable is changing. So the rate of change is just how quickly the variable is changing. And the other one is constant. Constant just means that it's changing, it's not changing. So what it means for two things to be in direct proportion is if one thing changes, the other thing changes in the same amount each time it changes that same thing time. Let me try that again. So when one of the variables changes, the other variable changes in a proportional or equal amount. So equal amount each time, so it doesn't change. Now, let's go through the second sentence. This can be graphed as a straight line. And so, straight line through the origin. Now, we talked about a couple lessons ago, straight lines that go through the origin. If you have a straight line that goes through the origin, it has the equation y is equal to mx. And m just happens to, and so with the m changes, the steepness of our line also changes. Now here, m, actually, in this section on direct proportion, m it's gonna tell me how quickly those two things are changing. So this is actually called the constant of proportionality. Constant of proportionality. So that's just the name of this particular variable that we're going to be, this letter or number that we're going to be talking about in this section. In the next section, we're actually going to name it something else, and you're going to see why, hopefully as well. So, just to give an idea of what direct proportion actually is about, I'm going to go through just an example just to help you think through what direct proportionality is about. So let's have a look here. So, Mr. Lee goes running at 6 meters per second. So I'm going running. Here's a real picture of me going running, definitely real. And I'm going very fast, zooming along. There we go. And there's a car, and the car is chasing me because I'm so fast. So there we go. And it's like, whoo, and Mr. Lee's too fast for the car. Okay, now Mr. Lee is running at 6 meters per second. Now, what this tells me, 6 meters per second, just tells me that every second that passes, I travel how many meters? 6 meters. So let's just talk about what this would look like. So here I have a table and I've got my time on my left hand column and the distance in the right hand column. So time in my left hand column, distance in my right hand column. So after 1 second, how far would I have traveled? Well, if I'm traveling at 6 meters per second, after 1 second, I would have traveled 6 meters. Okay, cool. After 2 seconds, how far would I have traveled? Well, after 2 seconds, I just go another 6 meters. So here I would have traveled 12 meters. Okay, let's keep going. After 3 seconds, I would have traveled how many meters? Well, I travel another 6 meters in the next second. So here this becomes 18 meters. And after the 4th second, I would have traveled how many meters? Oh, 24 meters. Okay, so let's actually talk about what's happening here. Let's talk about the time column first. Every time I go up in my time column, or down, in this case, we're going down in our time column, I'm adding on 1 second. Hopefully you guys can see that. I'm adding on 1 second. So between 1 to 2 seconds, I add 1 second. Between 2 to 3 seconds, I add 1 second. Between 3 to 4 seconds, I add 1 second. And in my distance, well, what happens to my distance as I go down my table? Well, every time I add 6. I'm adding 6 meters. I'm adding 6 meters. I'm adding 6 meters. And this pattern would hopefully continue if I keep that pace. Now, humans don't keep a regular pace. Unfortunately, we can't, we don't maintain regular paces for ever. We get tired and fatigued, but this is just for this example here. Now, this is an example of direct proportion. These two variables, so time is changing and distance is changing. These are examples of two variables. So these are my two variables. So these are my variables. And in my definition, what I wrote was, if the rate of change is constant, of one variable compared to the other is constant. Now, have a look here. Every time I go up by 1 in my time, every time I go up by 1, I go up 6 meters in my distance. That doesn't change. That doesn't change. As long as I maintain this 6 meters per second, that doesn't change. And so that's what it means to be in direct proportion. When one thing increases, the other thing increases, and as we keep increasing the same amount each time, that number, those rates of change do not change. So each time, I'm not going to expect to see suddenly in the next one, I'm going to add 7 meters. If one thing increases, the other thing increases the equal amount each time. So what we can do is we can actually graph this on my lines, on a Cartesian plane. So here, I've got distance in meters. So on my y-axis, I'm going to have d for distance. And on my x-axis, I'm going to have t for time. And I can actually plot this. Got 1, 2, 3, 4, 5, and so on. And the other side, I've got 6, 12, 18, 24, and so on. And so what I can do is I can just plot this on my Cartesian plane. I've got 1, that, and it forms a straight line that, what hopefully you notice, will pass through the origin. Well, if I can actually draw this. There we go, lined up. And so here, we've got a straight line that passes through the origin. So this is what we're talking about when we're talking about two things being in direct proportion. If one variable, the rate of change of one variable relative to the other is constant. My time is constantly increasing up by 1 second each time. And so my distance over those 1 seconds is increasing by 6 meters each time. And so we can actually create an equation for this line. What we said was it's going to be y is equal to mx. Now in this case, instead of y and x, we're going to have d and t. So here, this is just going to be d is equal to some number before my t. Now that number happens to be our gradient. So if you have a look at my line, my gradient, what we looked at last lesson was rise over run. If you have a look here, I have a rise of, for example, in this first part, 6 meters, and my run of 1 second. So here, this is going to be d is equal to 6t. Now 6 also just happens to be the speed that I was traveling at. So that's quite nice for us in these examples. So that's what direct proportion is about. If one variable changes in equal proportion each time with the other one. Okay, so let's actually have a go at answering a question on this. So this is example 1, and it's the only example we're going to be looking at because there's a few parts that are involved. So let's have a look at what this question's asking me to do. So here, water is poured into an empty tank at a constant rate. Now, if you see the word constant rate, that means it's in direct proportion. So this is the key word that indicates to you, oh, with the two things, I've got direct proportion here. It takes, let's read on, it takes 3 hours to fill the tank with 6,000 liters. So those are my next two keywords I'm going to underline. 3 hours, 6,000 liters. Okay, first part, A. Find what is the rate at which the water is poured into the tank. Now, what we want to find here is a rate. A rate is telling me how quickly is water being poured into the tank. So a rate asks you how quickly is something changing. Okay. Now, the information I'm using here is, well, it takes me 3 hours to fill up 6,000 liters. So my rate is going to be, okay, actually, I'm going to be comparing those two. So here, I've got 6,000 liters in 3 hours. And what I'm going to do is I'm actually going to divide it. When we are dealing with rates, we're going to divide. So here I'm going to have, okay, 6,000 liters divided by 3 hours. So this becomes 6,000 divided by 3 is 2,000 liters per hour. And so that's how we write liters per hour. Here, this is just liters per hour. Now, the reason I wrote liters per hour is because that's the units I have in this question. I am pouring in 6,000 liters of water, and I'm doing it over 3 hours. And so this tells me that every hour, I'm pouring in 2,000 liters every hour. So after the first hour, I would have poured in 2,000 liters. After the second hour, I would have poured in another 2,000 liters. And after the third hour, I would have poured in another 2,000 liters to get that total 6,000 liters. Okay, so that's this first example. Okay, part B. Draw a graph of the volume, V liters versus time. So T, hours. Using time is between 0 and 3. Okay, so let's have a go at this. So we're going to draw a graph. Just like I did in the example up above, I'm going to draw a graph to represent this scenario here. So, 1, 2, 3, 4, 5. Let's just do it here, and I'm going to go that. Okay, so what they want us to draw is volume versus time. So what I'm going to do is I'm going to draw volume on my y-axis. So this is V for volume. So I'm going to write here volume. And on this axis, I'm going to do T for time. Now, this example, time is in hours. So I'm going to just write down hours for my units. And volume, I've got L for liters. Okay, I'm just going to fill in a few numbers here. So for my time, it's between, they want us to do from 0 to 3 hours. So I'm going to go, okay, starting from here, 0, 1, 2, 3, and my volume, well, we go all the way up to 6,000, so maybe I'll put, hang on, 1, 2, 3, okay, excellent. I put 6,000 up here, then I go 0, and in between I've got 2,000 and 4,000, and we just want to make sure that our axes are even. Okay, so what I know is I start off at empty, and my other point is at 3 hours we poured in 6,000 liters, so I can just draw a straight line through those, which gives me, if I can draw a straight line, let me try that again. There we go. Here we go. Okay, cool. So there's my straight line. So this is my graph of my volume versus time. Okay, that's part B. We've drawn a graph that shows how my volume is changing over time. Part C. Okay, we want to find two things. Firstly, we want to find the gradient of the graph, and then the second part is we want to find the rule for V. So let's find the gradient of the graph. Now, gradient, if you remember, was rise over run. So let's actually do that. Now, in my graph, I've got this point over here, so I'm going to find the rise. And from here, I'm also going to find the run. So run. Now, my gradient is just going to be equal to rise over run. And that's what we looked at last lesson. So rise, let's have a look. Well, that's how many, the y coordinates. So in this case, we're looking at the volume. And so we actually go from 0 all the way up to 6,000 liters. So here that's 6,000. I'm going to write 6,000 here. Divided by the run, which is from 0 to 3. So my run is just going to be 3. So 3. So 6,000 divided by 3, that gives me 2,000. So here I get an answer of 2,000. Now, hopefully what you notice here is that my gradient is actually equal to my rate. My gradient is equal to my rate. That's the thing that to notice about direct proportion. Gradient and the rate are going to end up being the same thing. The gradient and the rate are going to end up being the same thing. Okay. The second part was we wanted to find a rule for my line. Now, what I said earlier was that the equation of a direct proportion line is y is equal to mx. Now for this one, because we're not dealing with y and x, we're going to actually need to change those numbers. So instead of y, I'm going to write, well, have a look at my y-axis. I'm actually measuring the volume. So here it's going to be v is equal to some number times, well, have a look at the x-axis. Instead of x, I've got t. So v is equal to some number times t. Now, the number before this t is just going to be my gradient. So here, this is just going to be 2,000. So my equation for my line is actually just going to be v is equal to 2,000 t. So let me just label that on my line. So v is equal to 2,000 t. So that's how we do this question. The equation of this line, because it is because it is direct proportion, it's just going to follow this pattern, y is equal to mx. And what we need to do is just change up the letters to match up whatever the scenario that we have is. And we just want to put in for m our gradient. Okay. That's part A, B, and C done. Let's have a look at part D. Now, part D. Use your rule to find the following. So we want to find, firstly, the volume after 1.5 hours and the time to fill 5,000 liters. Okay, so let me actually just write I'm just going to do it up here. My equation that I had was v is equal to 2,000 t. So let's have a look at part I. So D part I. We want to find the volume after 1.5 hours. Now, 1.5 hours, what is that? That is a time. So what I want to do here is I actually want to sub into my equation t is equal to 1.5. So let me just do that. So here for this first part, I'm going to go volume is equal to 2,000 t. That's my equation. And I'm going to substitute t is equal to 1.5. So I'm going to go 2,000 times 1.5. And you can chuck this in a calculator. I'm going to have here 2,000 times 1.5. So I get 3,000. So that tells me that the volume after 1.5 hours is 3,000 liters. So we can actually go to our graph and actually check that. So 1.5 hours is over here. And if I go up to my graph and just read off this value, well, and I go across here, well, this value over here would be 3,000 liters. So that's exactly what we should expect. Okay, that's the first question. Second one. Find the time to fill 5,000 liters. Now, 5,000 liters, what is that? Is that a value for t? Well, no. 5,000 liters is not a time. I'm not going to meet you in 5,000 liters time. That doesn't make any sense. So here, this 5,000 liters is not a time, but it's actually a volume. So what I'm going to need to do for the second part is I'm going to substitute v is equal to 5,000. So let's actually have a go at doing that. So here I've got part 2. I'm going to write my equation again. And I'm just going to substitute in 5,000 for my volume. So here I'm going to write, instead of v, I'm going to write 5,000 is equal to 2,000 t. And then from here, we need to start solving for t, like we did when we did our algebra topic earlier this year. So what we need to do, to get rid of that 2,000 from my t, I need to divide both sides. So I'm going to write here, t is equal to 5,000 divided by 2,000. And if you chuck that in the calculator, you end up getting 5,000 divided by 2,000, 5 over 2, or 2.5. So that's 2.5 hours. So what this tells me is if I want to fill up 5,000 liters, I should expect to do that in 2.5 hours. So let's actually have a look on my graph and do this. So for this one, I'm going to go to where 5,000 liters is, over here. So this is 5,000 liters, and I'm going to go across to my graph. Oh, it's over here. And drop it down. And over here, we get a time of 2.5 hours, which is exactly what that question told us we would get. So that's how we solve these questions with direct proportion. So let's just do a quick summary of what we talked about in this lesson. In this lesson, we talked about direct proportion. Two variables are in direct proportion if one, let me just put it up here, if the rate of change of one variable is compared to the other is constant. So when one thing increases, the other thing increases the same amount each time. So for example, we looked at me and my running, and we also looked at this example of volume, of water being poured into a tank. There's a few questions for you to have a go at to practice, which are fairly similar to this one that we had a look here. So if you're not sure how to answer a particular question, maybe you can look back at how we did it in this section here and just see how you can apply the same steps for your questions that you're doing. But as always, Year 9s, I hope you guys are staying safe wherever you are. And until next lesson, stay safe. Until next lesson, I'll see you then. Bye.